All right, we're going to be getting into Chapter 5, starting with the first section of 5.1, which is looking at trigonometry identities. So the first thing that we need to do is to define what an identity is in math, and what it is it's just a true mathematical statement. So another way of thinking of this is whatever the number or value may be, the answer always stays the same. So an example that I have here is an example of an identity, because if we were to go ahead and try and solve this problem, now there's a couple different ways that we can solve this. I'm going to go ahead and factor out my numerator to give me x plus 1 and x minus 1 divided by x plus 1 is equal to x minus 1. And with this, because we have a rational expression here over on the left, I can cancel out the factors of x plus 1, so we can get rid of those. This is now leaving me with x minus 1 is equal to x minus 1. And since I'm solving for x, if I went ahead and added 1 to both sides, my 1's are going to cancel out on both sides of the equation, which ends up giving me x equals x. And that right there is a mathematical identity. When you have something that equals itself, that's an identity. So no matter what value we put in for x, it's always going to stay true. So I could put in whatever number I want into my equation up here above, and every single number will work. So what we're going to be looking at now with our trig identities is different ways to write out sine, cosine, and tangent, and some different ways that we can write things out and still get the same thing, especially since we have this function that repeats itself, this sinusoidal function that repeats itself. We get a lot of the same functions over at different times. So I'm going to go first of all to some of the identities that we are already aware of, and that's the reciprocal identities. So in Chapter 4, we spent some time talking about the cosecant, the secant, and the cotangent. So we should feel really comfortable about these. And really all this is saying here is the reason it's an identity is because no matter what I put in for theta, I'm going to end up with two congruent statements then. So if I wanted to take the cosecant of 24 degrees, it's going to equal 1 over the sine of 24 degrees. We're going to get the same thing. Same thing with secant, same thing with cotangent. Now, what we also have here is we can think of sine, cosine, and tangent also as reciprocal identities. Just like the reciprocal of sine is the cosecant, well then sine is also the reciprocal of the cosecant. So this is just another way that we can come up with sine, cosine, and tangent. Now I'm not going to be require you to memorize any of these. I will be giving you a form in class that will have all these identities on them, but I just want to go through and with this video today explain where some of these come from. The quotient identities that we have is based off of tangent and cotangent. Tangent we know is taking the sine divided by the cosine, and cotangent's the reciprocal of that, which is cosine over sine. Doesn't matter what we put in for theta, it's going to hold true. So what this leads me to is the Pythagorean identities, and this is probably one of the most important identities that we're going to be getting into throughout this chapter. And when we've been talking about our sine and cosine in our unit circle, we've been looking at a unit circle that has a radius of 1 unit. And we have found that at any rotation of theta radians or theta degrees, as I rotate this point, which started out as 1, 0, as I rotate this point around my circle, I end up with an x-coordinate and a y-coordinate based off of the sine and the cosine of the angle that it's rotated. Well, from this then, we have been talking about how your x value, which is always in relation to the cosine of theta, and our y value is always going to be our sine of theta. Well, now I have a right triangle sitting in here in my circle with a hypotenuse of 1. And then if I think back to my Pythagorean theorem, where a squared plus b squared equals c squared, this is telling me that if I were to take cosine squared, so cosine theta squared plus sine theta squared, I'm going to get 1 squared. And what this is telling us here is this is what's called our Pythagorean identity. taking cosine squared plus sine squared will always get us 1, since the radius of our unit circle is always going to be 1. Now we write this out slightly different in most textbooks, and as we'll see it. So instead of using parentheses and putting the 2 out in front, you'll take the square and actually put it after the cosine. You'll see it written out this way. And all this is saying is cosine theta squared plus sine squared theta is equal to 1. So this is our Pythagorean identity. Cosine squared theta plus sine squared theta equals 1, or sine squared theta plus cosine squared theta equals 1. Now with this Pythagorean identity, I can also create 2 other identities to go along with it. We could create one here saying that the cosine squared of theta is equal to 1 minus the sine squared theta, just because I'm solving for cosine squared theta. And we could also do the same thing if we wanted to solve for sine squared theta, where I would take 1 minus the cosine squared theta. This is just 3 different ways that we can write out the Pythagorean identity. And these 3 ways we're going to be using quite a bit over the next couple days. Now there are an additional 2 Pythagorean identities that I'm going to write down as well. And over the next couple days we will see where these identities are coming from. One of them is 1 plus the tangent squared theta, which is equal to the secant squared theta. And the other one is going to be the cotangent squared theta plus 1 is equal to the cosecant squared theta. So these are also 2 Pythagorean identities that we're going to be working with, and we will be figuring out later in class of how we actually get that answer from the problem. So an example of where we can use Pythagorean identities. Here I have an example where it says find sine theta and tangent theta if I'm given that the cosine of theta equals 0.6 and the sine of theta is less than 0. So we had a problem very similar to this back when we were just starting our trig unit. And when we're solving this one here, I can use the Pythagorean identity to help solve it. Since I'm given cosine and I want to find sine, using sine squared theta plus cosine squared theta equals 1 will help me do that. So here I can take sine squared theta plus cosine squared theta, which is 0.6 squared, is going to have to equal 1. So now I have sine squared theta plus 0.36 is equal to 1. If I subtract 0.36, I'm going to get the sine of theta is equal to 0.64. And just like when we solve a Pythagorean theorem, to get rid of that square, I'm going to take the square root, giving me that sine theta is equal to plus or minus 0.8. Plus or minus because we can either have a positive value or a negative value of 0.8 to get the 0.64. So now this is telling me 2 answers. And here, if I'm just trying to find sine theta, I'm going to look at the piece of information that's given to me here to help me figure out if it's going to be the positive 8 or the negative 8. Cosine theta here is 0.6. The fact that that right there is positive tells me that I have to be either in the first or the fourth quadrant. Because of sine theta being less than 0, that tells me I have to either be in the third quadrant or I have to be in the fourth quadrant. Of these 2 values, the one that they both have in common is being in the fourth quadrant. So if I'm going to be in the fourth quadrant, that tells me that my sine of theta here has to be less than 0. So now sine theta is not going to be positive 0.8, it's going to be negative 0.8. This is going to help me now find my tangent. Since the tangent of theta is sine over cosine, I've got my sine value, which is negative 0.8, divided by the cosine, which is positive 0.6. And once I work this out, I end up with negative 4/3. And when I think about being down there in the fourth quadrant, having it be negative 4/3 is a good thing because our tangents are negative down in the fourth quadrant. So this is just an example of how we can use the Pythagorean identity to help us solve a problem. Moving on to another type of identity, which is the cofunction identities. Here, if I have my right triangle with angles A, B, and C, I've got sides of X, Y, and R. I've already gone ahead and written out the 3 trig ratios for angles A and angle B. And as we look at these, one thing I'd like you to notice here is that if we take the cosine of angle A, it equals X over R. Well, that is the same thing as the sine of angle B, which is X over R. Then if I look at cosine of angle B, which is y over r, that's the same thing as the sine of angle A, which is y over r. What's happening here is if we look at angle A, if I knew what angle B was, I could find angle A, because I already have a 90-degree angle here, by taking 90 minus the measure of angle B, and that would give me angle A. In the same kind of way response here, angle B, if we take 90 degrees and we subtract angle A from that, we're going to get the same thing. That's exactly what's going to be happening with our next identities here. However, instead of using 90 degrees, we're going to use radians. So we're going to use pi over 2 minus angle B. And we're going to end up taking here pi over 2 minus angle A. And this is going to end up giving us some new identities here of showing that we can have sine and cosine being equal to each other as long as we change one of the other angles. Now this also works with tangent and tangents of the two, but we have to look at the cotangents. If I were to take the cotangent of angle A, I would be getting x over y. If I were to take the cotangent of angle B, I would get y over x. And so with our tangents then, our tangent of angle A is equal to the cotangent of angle B. And along with that, our cotangent of angle A is equal to the tangent of angle B. And so now, how we got those angles, again, is taking pi over 2 minus theta. And here's now our cofunction identities. So by taking the sine of pi over 2 minus theta, that ends up equaling cosine. Okay, what I'm doing here is I'm just taking a look at two different angles. I'm saying the sine of angle A equals the cosine of angle B. And all we're doing is we're just changing those two. The cosine of angle A equals the sine of angle B. Because those are changing, the pi over 2 minus theta gives you that different angle, the one that's just going to be opposite of it. So we have this with our tangents and our cotangents, and then we can work our secants into it as well. So our secants are just coming from working with our original here, the fact that actually I should have this the other way around, just the fact that we have our secant of pi over 2 minus theta equals a cosecant, so then the cosine, it's going to be the opposite. It goes along with our cosine, same thing. So an example of how we can use this information. If I am given that the cosine of theta equals 7.5 and I want to find the sine of pi over 2 minus theta, well, we know that the cosine of theta equals the sine of pi over 2 minus theta. So here, if cosine of theta equals 0.75, we really do not have to do much work, and we can go ahead and say that the sine of pi over 2 minus theta equals 0.75 as well. All right, on to our next identity, which is going to be our even and odd identities. You know, thinking back to what does it mean to be an even or odd function. Remember that odd functions have rotation symmetry. Even functions have y-axis symmetry. So the first one here has, which is our sine function, this is a function that has rotation symmetry. We can rotate it 180 degrees, it will be the same graph. Our cosine function has even symmetry to go along with it, since it can be reflected across the y-axis. And our tangent function is going to have the odd symmetry because it can be rotated as well. Going down to our cosecant and cotangent, here I have my cosecant, which is going to have rotation symmetry, so it's going to be an odd function. Then we have our secant function, which is going to have y-axis symmetry, making it an even function. And then our tangent function here does not have y-axis symmetry. It's got rotation symmetry, making it an odd function. So if we recall how we come up with our even functions and our odd functions by using f of negative x, remember that f of negative x, if it equals negative f of x, then you have an odd function that takes over, that reflects the rotation symmetry. And if you take f of negative x and that equals f of x, that takes you with your y-axis symmetry. So if we take all of this and we put it into our identities of sine, cosine, and tangent, we have our even and odd identities. So the sine of negative x, okay, because here we have our, with our sine function, that's going to be our odd function. When I put a negative in for it, then that gives me negative sine of x. Cosine, which is going to be even, ends up being cosine of negative x equals cosine of x, because it's going to stay the same. So here I have f of negative x equals f of x. Here I have f of negative x equals negative f of x. With tangent, here it's, since it's an odd function, f of negative x equals negative f of x, and that's where the negatives come into play. Same thing with our cosecant, secant, and cotangent. So when we start to look at just a couple little examples of this one here, if I have the cosine of theta equals 0.34, if I'm trying to find the cosine of negative theta, that's the same thing as cosine of theta. So that means that it would have to equal 0.34. They have to be the same value. Taking the sine of negative theta, the sine of negative theta equals negative sine of theta. So since sine of theta is negative 0.41, I'm going to end up with a positive 0.41. Now the next one here can be a little bit tricky to look at. I'm given that cosine of theta equals 0.27, and we need to find the sine of theta minus 2 pi. Well, theta minus 2 pi, we have to be careful here because it's not the same thing as what we were doing the other one with our cofunction identity, because that is pi over 2 minus theta. So what we can do here is we can kind of switch this up a little bit, and since we're trying to find the sine of theta minus pi over 2, what we can do here is by taking the opposite of that, so taking the function of f of negative x, we're going to end up here with taking the sine of negative pi minus, or theta minus pi over 2. And because I'm taking the sine of a negative, what that's going to happen is that's going to make my sine value actually negative. So I get negative sine, and inside when I distribute this, this is actually going to give me pi over 2 minus theta. It's going to make that pi over 2 positive, giving me theta to be negative. Well, sine of pi over 2 minus theta is equal to the cosine. And so here I end up with negative cosine, which started out with the sine of theta minus 2 pi. Since I'm given what cosine is of 0.27, my final answer then is negative 0.27. And that right there is the sine of theta minus pi over 2 if given cosine equals 0.27. So we've just done an introduction to our trig identities, and where this is all going to lead us is, let me see where I'm at time-wise. Okay. Our goal in the next couple days now is to simplify some trig identities. And what I mean by that is we're going to use the identities that we were just talking about and try and simplify things so we can get it down to one trig function rather than two things here. I'm going to go through two examples and then we'll do many more in class. But here I have tangent of x times the cosine of x. Well, the tangent of x is the same thing as sine over cosine x. If I think of this now times cosine x, which would be over 1, when I multiply fractions, my cosine x's are going to cancel, leaving me with sine x over 1, which simplifies down to sine x. So the tangent of x times the cosine of x can be rewritten as the sine of x. One more example, taking the sine x to the third power plus sine x times cosine x squared. We can always use our properties of factoring with the problem here. You know, think of this right here as x to the third plus x times y squared. We can take an x out of the problem, leaving me with x squared plus y squared. So by doing that, I'm going to take out a sine out of both of them, a sine x, leaving me with sine squared x plus cosine squared x. And now one of my Pythagorean identities says that sine squared x plus cosine squared x equals 1. So now I have the sine of x times 1, which when I multiply that out, I get sine of x. So we will spend some more time practicing these trig identities, but again, I will give you a piece of paper that's going to have you have all of them on there for you, so you don't have to worry about that part. And we will spend some time working on simplifying these because it will take a little bit of time. If you have any questions on anything, please let me know. I know that I went through the identities and the explanations of them fairly fast, so let me know if you could, if you need something explained to you a little bit slower.